This ship has a problem, and it's not a very unusual problem either. It's shared by quite a number of ships. The problem is one of low-frequency vibrations caused by some cyclic force. Now, in this case, the cyclic force comes from the action of the propellers. It may be, in cases like this, that the cyclic force causes resonance, or at least uncomfortably large vibrations, in some part of the structure of the ship. In this case, the trouble is on the floor of the car deck. Well, we're at sea now, and this great expanse of metal floor has a very low natural frequency, and that's part of the trouble. Its natural frequency isn't very far away from the frequency with which the propeller blades strike the water. In terms of mechanics, you can think of this car deck as a spring mass system. And you know that when a cyclic force acts on a spring mass system at a frequency near to the natural frequency, we're liable to get resonance. Of course, if we change the stiffness, or if we change the mass, the response will be different. And you might well say that if this ship had been designed with a different sort of deck, or a different type of propeller, then all these troubles would never have arisen in the first place. And you may well be right. But it's too late now to redesign the ship, and we can't make big structural alterations. We'll have to cope with it as it is. Now, as a matter of fact, there is a way of dealing with the problems of vibration here, and a major part of this program will describe one of these plans. But before we do that, let's just have a look at these vibrations. This is a vibrometer, and I can use it to measure vibrations. Now, a vibrometer is a simple device which measures frequency, and it consists of a case which is put in contact with a vibrating surface and a metal strip which projects from the case at a variable length. Now, every length of projection resonates at a different frequency, and there is a scale on this instrument which is calibrated in terms of the frequency of resonance of each length of projection. At the moment, for instance, nothing much is happening, but if we make the length a bit bigger, sooner or later we'll get resonance. There's resonance here now, at a frequency which the scale says is about 13 hertz, or 13 cycles per second. Now, similar measurements to this, only rather more elaborate, were made by Southampton University some years ago. This ship was called Viking 2 in those days, and the major thing we're going to look at in this program is their proposal for a vibration absorber to cope with the vibration of this very car deck.
The ship's operators came to us with this vibration problem, excessive vibration of the stern deck. And it's a common problem in ships. So we thought we could absorb this vibration by adding another degree to the deck, another degree of freedom system to the deck, a vibration absorber. But the classical vibration absorbers were lumped masses, heavy weights of iron or concrete supported on springs. These springs eventually fatigued and broke, and the whole thing was rather unsatisfactory. So we thought up this idea of using water as the absorbing mass and using an air spring as the spring for this second degree of freedom system. Now, this is a simulation of the Viking 2 car deck, and the vibration generator represents a forcing function which on the ship itself would be caused by the propeller blade passing frequency. As the propeller blades pass the hull, it excites the vessel. I'm now going to absorb the vibration of this single degree system by adding to it another degree, making it a 2-degree vibration system, and we'll then tune it in such a way that the energy which you saw being generated by the single degree freedom system will be absorbed by the second degree of the two-degree system. The deck is the one-degree system, and you can see at this particular frequency the deck vibration is very small, not 100% reduced, but certainly very much smaller than it was. Whereas the second degree part of the system, the mass of water bouncing on an air spring, is vibrating in a fairly agitated fashion, indicating that the energy from the deck is being absorbed by the water here.
Now, in this program, we want to construct a mathematical model for the system. Now, our system consists of a springy car deck, and when the propellers of the ferry boat start to go round, then the deck springs up and down. Now, we can actually get rid of that bad behavior by adding a contraption of water and air, which I'll represent by a spring in this device. Well, that seems to do some good. Now, we can actually capture the essential ingredients by this system of two springs. Well, the mass spring system here represents the springy car deck, and the second mass spring system here represents that contraption of the mass of water bouncing on the spring of air. Now, what about the motion of the propellers? Well, I'll represent that by a forcing function. That's that red arrow. Well, that's what it looks like mathematically. Now, we can actually reproduce this experimentally.
This is the complete system, and here is an identical system, but without the vibration absorber and its spring. Both of these two systems are subject to the same amount of forcing. And you can see the amount of difference that the vibration absorber makes. So what do we make of all this? What we want is a mathematical analysis of this behavior.
Well, we'll get that mathematical analysis by the end of the program, but we've a lot of modeling to do before then. First of all, let me remind you of some things that you already know. We know how to treat a system of 2 degrees of freedom without a forcing function. So let's take this forcing function completely away and remind you how to treat this system. Well, I have a mass MA, a spring of stiffness KA, a second mass MB with spring stiffness KB, and remember, we'll measure the displacements of the mass from its equilibrium position in both cases. And we write down Newton's equations, and we have these two second-order differential equations. Well, how did we solve them? Remember, the assumption we made was that the acceleration, x double dot, is proportional to omega squared x in both cases. That means that we simply replace the right-hand side by this and that in each case. Well, this assumption really tells me that I'm assuming that each mass is performing a simple harmonic motion with the same frequency, omega.
Well, that's quite possible. Both masses move with the same frequency, and in free vibration this time. The top of the upper spring is stationary.
Well, as I said, you've seen this before, and you probably also remember that the equations look neater in matrix form. And in matrix form, it's easier to see that these omega squareds here are just what we call the eigenvalues of the matrix. Now, you get the eigenvalues from the characteristic equation of the matrix. That's got by putting the determinant of the matrix equal to 0. Now, when you do that, you're going to get a quadratic equation for omega squared. So what we're going to get is essentially 2 frequencies. Well, what do these frequencies mean?
Well, they mean exactly what they say. 2 characteristic frequencies of the system called the normal mode frequencies. And here they are. Here's one, and there's the other. Now that one's at a higher frequency, so that's omega 2, and this is omega 1. Now here, both the masses are moving with simple harmonic motion at the same frequency, and their motions are in phase. Whereas here, they are still moving with simple harmonic motion, but they are phase opposed. Now, will I get sinusoidal motion for all free vibrations of this system? Well, the answer is clearly no. But even when the vibration is non-sinusoidal, the normal modes are still important, because it's a property of the normal modes that any free motion of the system is a linear combination of the normal modes. Suppose the spring mass represented here is released in such a way that it oscillates in the first normal mode. And the initial conditions of an identical spring mass system are such that it oscillates in the second mode. Linear combinations of the two, as in this third system, don't look sinusoidal at all. Look at that again. Three different linear combinations. Concentrate on the absorber mass, for example. Its motion is nothing like sinusoidal.
The fact that the normal mode motion is sinusoidal is the assumption that I made in the first place in order to obtain the normal modes. Well, the value of normal modes is, as Dick said, every free motion of the system can be obtained as a linear combination of the normal mode motion. Well, I find it absolutely fantastic. And in fact, for a system of 2 degrees of freedom, we get them as the eigenvalues of a 2 by 2 matrix. And you can guess for a system with 3 degrees of freedom, we'll get the normal modes as the eigenvalues of a 3 by 3 matrix, and so on. So all we have to do is to get the eigenvalues of a bigger matrix for a more complicated system. But that's another story. Now, we mustn't lose sight of our original problem, how to get rid of unwanted vibrations. Well, we're still interested in a system with 2 degrees of freedom, but let's go back to our original problem in which we had a forcing term present. Remember, I represented that forcing term graphically by an arrow, but how am I going to represent it mathematically? Well, I'll assume that it's given by a displacement of the point of suspension, y, which is proportional to a sinusoidal term of frequency large omega. Well, if I look at my equations of motion, and I make this substitution, in fact, it turns out, and you really have to do this for yourselves, that the only change necessary in these two equations of motion is simply to change this xa to xa minus y. So that's the mathematics of the situation. Now, what does this mean experimentally?
Well, here's how our system behaves when a steady sinusoidal motion is imposed on it at the top. And when it eventually settles down, both masses are moving with the same frequency, and indeed with the same frequency as the forcing motion.
Well, actually, that gives me the clue I need in order to solve these equations. Remember what Dick said, when the system settles down, that is, in the steady state, everything is going at the same frequency as the forcing motion, large omega. That means I can substitute for x double dot a simple harmonic motion of frequency omega. That means this must be proportional to large omega squared x. And a similar expression for the second. So that enables me to replace my differential equations by a simple pair of algebraic equations which I can solve. Well, I can solve for what? What am I interested in? Well, I'm actually interested in the motion of the deck. Now, the motion of the deck is the displacement xa. So what I have to do is to solve these algebraic equations for the term xa. And this is the solution for xa. Well, it looks pretty gruesome, but actually you can get it by rather simple algebra, which I rather you did after the program. From this expression, you can actually get some of the features just by inspection. Let's see what they are. Well, let's look at the denominator. The denominator is a quadratic in omega squared. And that's got two roots, so there are two places where this quadratic is going to vanish. Now, when that happens, that means the whole thing blows up. We've got resonance. Now, it turns out that the two frequencies for which you get resonance are just the normal mode frequencies of the free system. Well, that's rather interesting. But we're actually more interested in the condition for which the deck doesn't vibrate. In other words, this term has to be 0. Well, that'll be 0 if the numerator is 0. Well, the numerator could be 0, of course, if this vanishes. That is, if we have no forcing term. But we actually have a forcing term, so this option isn't open to us. So you've got to look at the bracket. And that's the condition for vanishing, if the bracket vanishes. And that will happen when this is satisfied. And that really gives me the parameters of the vibration absorber in terms of the given forcing frequency. And that's a rather simple, interesting result. Well, they say a picture is worth 1,000 equations, so what I'm going to do now is actually draw a graph which corresponds to this and see what we can get from the graph. What I've actually plotted is amplitude. Now, amplitude is the maximum value of xa against frequency. And here we see the typical graph of a system with 2 degrees of freedom. It's got 2 peaks corresponding to 2 resonances. See, if I had a system with just 1 degree of freedom, then I'd get a single resonance peak. And if I had a system with 3 degrees of freedom, well, guess what I'd get? I'd get 3 peaks, and so on. And by the way, these peaks actually do go on to infinity because I don't have any damping in this theoretical model. Well, let's get back to our 2-degree system. And the interesting fact for us was that between the 2 peaks, we actually had a trough where the amplitude went to 0. And at that trough, we had the condition for a vibration absorber.
So I'm now going to sweep through the frequency range to pick out the 2 peaks which we would expect to see for a 2-degree system. I'll sweep the frequency range up through, this is 11 hertz, 11.1, 2, 3, 4. Here we have the maximum excursion, about 11.7 hertz. This is the first peak. I'll now carry on increasing the frequency to find the second peak. Meanwhile, I go through the trough between the 2 peaks, around about here. And here is my second peak coming up at around about 20, 22, 20, almost 23 hertz is my second peak, slightly lower than the first one because it's not strictly a linear system. I can now sweep back again to find the quiescent position between the 2 nodes at around about somewhere between those 2 peaks, say here. And here I have probably my best condition where the boat amplitude is a minimum and the vibration amplitude is building up here, indicating that the 2nd degree part of the system is absorbing the energy of vibration of the boat model. Well, the advantage of this device is that any machine, vessel, ship, car, aeroplane, having been built, is found to resonate at an awkward operating frequency. It's too late to drastically modify the design of the ship, but it's quite a simple matter to add this 2nd degree to the system. So on the ship, it happens to be that water is the the most efficient way to do this, but on other vessels, other machines, aircraft and so on, it may be better to add a lumped mass in the normal way. It could be a weight on a spring, which could be linear or non-linear, and so on. But the further developments on the ship, we expect would be in this way. Basically, the Den Hartog absorber is a precisely tuned system. So whilst the ship is crossing the channel, say, at a steady speed, 20 knots, there's no problem. It's tuned to absorb the vibrations. But as the ship approaches harbour or comes up to Solent, then the engine revs reduce, and we want to be able to fit a feedback system to this absorber so that the deck vibration can be monitored. As the deck vibration begins to increase, meaning that we've gone off tune, then the feedback system will admit more water, so increasing the mass of the absorber, and so retuning it for the new forcing frequency.
So there you are. A feasibility study, if you like. The idea was never put into practice on this ship, but there's no doubt about its potentiality for vibration absorption. So what have we seen in this program? We've seen the free vibration of 2 degree of freedom systems. We've seen the superposition of their normal modes. We've seen the forced vibrations of a 2 degree of freedom system and their application to vibration absorbers.